All right, let's get into it. If you're doing GCSE physics, you know some things are just guaranteed to pop up on the exam. Well, today we are cracking open one of the big ones, the required practical on springs. This isn't just about messing around in the lab, it's a direct route to scoring some serious marks, and we're going to break down exactly how you can nail it.
So, here's our game plan. First, we'll cover why this practical is basically a gift for your exam revision. Then we're going to dig into the science of stretching before walking through the exact method step by step. After that, we'll see how to turn our raw numbers into a really powerful graph. And finally, I'll show you how to analyze your results to make the examiners sit up and take notice.
Okay, Section 1, why this practical matters. Let's connect the dots between what you're doing with the equipment and what you're going to be writing on that exam paper. So let me just ask you this. With a subject as massive as physics, how can you guarantee where any of the marks are going to come from? It can feel like a total guessing game, right? Well, actually it's not. The answer is kind of hiding in plain sight.
And there it is. The exam boards, like AQA, they literally tell you your final exams will test you on these required practicals. They're going to ask about the method, the data, the analysis, the whole shebang. So think of this session not just as revision, but as direct prep for questions you know are coming your way.
All right, moving on to Section 2, the science of stretching. Before we even think about hanging weights on a spring, we need to get our heads around the physics. Because trust me, once you understand the why, the how becomes so much easier. You know, this whole experiment really hangs on one key idea, elastic deformation. It sounds fancy, but all it means is that an object, like a spring, can be stretched, and when you let go of the force, it snaps right back to its original shape. That's it! And this slide really shows you the crucial difference. On the left, you've got that elastic change. It's temporary. But on the right, that's an inelastic change. It's permanent. It's like when you overstretch a plastic bag and it just stays all baggy. If you stretch a spring too far, it's not going to go back. For our experiment to work, we've got to stay in that elastic zone.
And this is the beautiful little equation that pulls it all together. Hooke's law. It looks so simple, but it's incredibly powerful. The force you apply, that's F, is directly linked to how much the spring stretches, which we call its extension, or E. And that K in the middle, that's the spring constant. It's just a number that tells us how stiff a particular spring is. Oh, and a huge exam tip. You have to make sure your extension is measured in meters.
Okay, Section 3, let's get practical. It's time to talk about the method. Getting these steps right isn't just about getting good, reliable results. It's about doing the whole thing safely.
First up, your toolkit. You're going to need a clamp stand, the spring itself, a good meter ruler, and a set of those slotted masses. But honestly, the most important piece of gear on this slide has to be the safety goggles. Seriously, don't even think about starting without them. Right, the procedure. As you can see, it's a nice, straightforward 6-step process. You set everything up and get that super important initial reading of the spring's length. Then you start adding the masses, just one at a time. After each mass, you measure the new length, figure out the extension, and write it all down. The real key to getting good data here is just being consistent and methodical.
Just a quick but really vital word on safety. Like we said, goggles are totally non-negotiable. You also want to make sure that stand is clamped down or has a counterweight so it can't fall over. And remember what we just learned about the elastic limit? Don't go past it. If you overstretch the spring, you'll ruin your results and you could damage the equipment.
Okay, Section 4, from data to graph. You've done the experiment and now you've got this table full of numbers. So what, right? Well, now we turn that raw data into something much more powerful, a graph that will visually prove the physics we've been talking about.
Your results table needs to look something like this, nice and clean, super organized. Make sure every single column is labeled with the correct units. Now the column we really care about for our graph is that final one, extension. That's what we're going to plot against the force. And please, don't forget that crucial step. Get everything into standard units, newtons and meters. Now even with a simple chart like this, the pattern just jumps right out at you. Take a look. When the force doubles from 1 newton to 2, the extension also doubles from 0.02 to 0.04 meters. See that? This is a massive clue. This is the relationship that we are hunting for. And here it is. This is the money shot. When you plot these points on a proper graph, with force on the y-axis and extension on the x-axis, you should get a perfect straight line that goes right through the origin, 0.00. This isn't just a tidy graph, this is the visual proof of Hooke's law. It literally shows us that force and extension are directly proportional.
And that brings us to our final section, and it's a big one: acing the analysis. This is where we go from a good grade to a great one. It's all about looking at your results like a proper scientist and thinking critically about what it all actually means.
So, what would happen if you did add too much weight? Well, you'd hit something called the limit of proportionality. This is the exact point where the spring basically gives up and stops obeying Hooke's law. On your graph, that beautiful straight line would suddenly start to curve away. Being able to spot and explain that's a top-level answer right there.
Now, that straight line isn't just for show. The steepness of it, what we call the gradient, it actually is something. The gradient is the rise over the run, right? Well, in our case, that's force divided by extension. Now, think back to our equation. F equals K times E. If you rearrange that to find K, you get K equals F divided by E. The gradient of your graph is the spring constant. You can literally calculate the stiffness of your spring right from the graph you drew. How cool is that?
To really get those highest marks, you've got to be able to talk about errors. You might have random errors, like parallax error from looking at the ruler from an angle. You can fix that by always keeping your eye level with the reading. Or you could have a systematic error, maybe from a ruler with a worn-out end, which makes every single one of your measurements slightly off. And the best way to improve your results overall? Take repeat readings for each mass and then calculate the average. It makes your final data so much more precise.
And look, don't just take my word for it. This is what we're aiming for. The AQA specification itself says an accurate measurement is one that's close to the true value. Everything we've talked about, reading carefully, clamping things down, taking repeats, it's all designed to get us closer to that true value and to prove we've worked accurately.
Okay, let's do a quick-fire recap of the absolute must-knows for your exam. Number 1, the extension of a spring is directly proportional to the force you apply. Number 2, the equation is F equals K times E. Number 3, the gradient of that force extension graph is the spring constant K. 4, know the difference between elastic and inelastic. And finally, number 5, be ready to talk about errors and how to improve the experiment. You nail those 5 points and you're in a fantastic position.
So, I'll leave you with a final little challenge to chew on. We've totally mastered a single spring, but what if you took 2 identical springs and attached them side by side, then pulled on both at once? Would that whole system be stiffer or less stiff than just one spring? In other words, would the combined spring constant be higher, lower, or the same? Have a think about it. Answering that question, that's the next level of understanding.